Okay, so different types of circuits. I'm actually going to jump back one. So let's cover a few circuits. Series is the most simple. This is the one that we've already spent kind of a lot of time on. But take a look at series, look at it, and then take a look at parallel. Can anybody point out the major difference? It does, but I could actually make the series circuit have two loads. They would just have to be in line. So I could have a bulb and another bulb. That would be series even though it has two loads. Whereas parallel has two loads, but why are they different?
One splits into two different lines.
Yeah. There you go. So the way to think about the parallel to me, multiple lanes. In a series circuit, there's only one lane. So as many load, think of the load kind of as like a stalled car. If this is a stalled car, this is going to slow down all the electrons that are in this single lane. There's only one lane. So if we add another stalled car, do you think that's going to slow it down even more? Right. So every load that you add in a series basically reduces the amount of cars flowing, which is like reducing the electrons. What's that mean for the amps? We add a load, what's that do to the amperage of the circuit? Think about it. The load is a stalled car. So if we add another stalled car and another stalled car, it's just going to go slower, slower, slower. Yeah, exactly. It's going to be like a big traffic jam. So the way you want to think about this is every load that you add is going to consume more voltage and it's going to lower your amperage. The reason that's so critical is right here we have one load, right? And we could describe it in two ways. So I'll give you the first one that's simple. The truck driver, remember the truck driver with the big trailer, and he's like, yeah, let me add more lights to make my truck look cool. For every bulb that this truck driver adds, what's that going to do to each bulb? Like let's say that you had one and now you put two. Are they both going to be bright? Yeah, heck yeah, it'll dim it because they've got to share the available 12 volts. So this bulb used to get 12 and it was all bright and proud. And then we add another one and it's like, oh, I only get 6.
So you don't have to add a higher fuse?
No, because this is just going to keep reducing your amps, reducing your amps, reducing your amps. Cool? Now, and so that's what's kind of funny is for every load you add in series, it slows the amps down, kind of like an additional stalled car, right? And the other way that's like the truck driver, you're modifying, you're engineering the circuit way to look at it. Every load that you add will make the bulb more dim and it'll make your amperage lower. It's not even close to blowing the fuse now. This maybe was flowing 4 amps. If you add another bulb, it's probably going to flow 2 amps. It's not even close to blowing the fuse. But in automotive, we're not normally, the day-to-day activity for the cars that roll into the shop is not, hey, I want to add more lights. What it really is, hey, I got a problem with my circuit. So if it's a light bulb and it's dim, that would be why it would come in the shop. They'd say, I got pulled over. The police officer said that my taillight's out or dim or whatever, and I need to fix it. It's not the norm that the customer comes in and says, I want to add 4 lights onto my circuit. See, that's just not every day. Cool. So if you think about this, if this light bulb was dim, that would probably mean the amperage is too low, right? That's one way to look at it. And the other way to look at it, if this light bulb is dim, it's not getting the full available 12 volts. It's probably sharing the voltage with someone, wouldn't you say? Now, where's the unwanted load? It's not even really a load, it's just unwanted resistance. So if we're expecting 4 ohms on this bulb, and this bulb is only consuming 6 volts, that would mean there's another 4 ohms somewhere in this circuit. Where is the unwanted resistance? Well, maybe it's the switch, maybe it's the ground, you're right. But the thing is, you got to test for it, right? So everything that you learned, how to test voltage and voltage drop, available voltage, voltage drop, how to test amperage, how to test resistance. The only reason that we cover those is so that ultimately when you have a problem in the circuit, you have multiple tools available to you to be like, it is the switch, it is the ground. Not like it could be, you're right, it could be the switch, it could be the ground, but like, Do the measurement and prove it to me. You could prove it to me in several ways. So if we have a bulb that's dim, you could come in here and you could be like, what's the available voltage? Oh, the available voltage is 12. Afterwards, the available voltage is 6. And you're like, no, wait a minute. It should have dropped to 0. That means if there's still 6 volts available, there's something consuming the 6 volts down here. You kind of know it's got a bad ground and you're focused on the ground side. Or the other way you could do it, which is not the preferred way, but I'm just saying you could disconnect the positive, close the switch, and you could measure resistance in ohms, right? This should be like 0.2 ohms. This should be 0.2 ohms or less. This should be maybe potentially as high as 0.5. This wire should be 0.2. This bulb should be 4 ohms. And this ground should be 0.2, but instead you find the ground is 4 ohms, right? So you proved the ground was bad in 2 different ways. You proved it was bad by available voltage, or you proved it was bad by measuring resistance. Available voltage is more it's the stress test, remember? That's the more accurate one, right? But the whole reason that you want to understand those measurements and you have to understand the theory so well is because you have to know what tests to apply to this. So if we were to go back to the very first day and I were to say, hey, I've got a dim bulb right here, consider this to yourself. Would you know even where to start? You'd be like, maybe change the bulb, but that's where we all start. We all start there, right? We're little babies and we're like, you can't even handle solid food yet. So you're like, change the bulb. And that's it. And then if that doesn't fix it, you're like, I don't know, maybe throw a new switch in there with the parts cannon. And so that's fine when you're DIY and you're interested in wasting your own time and money, that's fine. But you can't be doing that for a customer. You can't be like, well, it could be, go to the doctor and say, doctor, I have headaches and stuff. Well, it could be brain cancer. Cool. Do you want to start treatment? Like, did we do any tests? That's not how we, as the professional, that's not how we do diagnosis. We don't say, could be this, could be that. Let's start the chemotherapy for the brain cancer that hasn't been verified. Make sense? So we're going to do some of those measurements. Cool. This is your bread and butter right here, series. We're generally troubleshooting with a series brain. However, let's say we're over here on the parallel. The way that we troubleshoot the parallel is just a little bit different. So let's go back to the truck driver. Truck driver's like, I want my trailer to be really lit up so I can impress people at the truck stop or something. I don't know. And they're like, let me add another bulb. See, if you add a bulb in parallel, remember we did the math and I really struggle with the math and it's not that I couldn't be really good at the math. It's just, you guys heard the saying, you want to prune the vines that don't bear a lot of fruit. Me doing the math doesn't really bear a whole lot of fruit, so I kind of let that one go. I came a little unprepared, but what I can tell you is the practical application. If the truck driver adds an additional bulb, that's reducing the overall resistance, which means it's increasing the overall amperage. Why is that so critical? For every bulb the truck driver adds, it's like adding another lane to the highway. So you had one lane, right? If you add stalled cars, okay, no problem. But if you add a stalled car, but you also added another lane, overall, you're going to increase the amps, wouldn't you say? Right? Because now you don't have just one lane going slow. These lanes may be going a little slow, but see, there's cars here and there's cars here. But back up. Look at what's different. There's 2 lanes here, but what about up here where the fuse is? There's still only 1 lane up there. So these cars are going to have to go twice as fast. One's going to go over here and one's going to go over here. Make sense? So if you had, rough numbers, if you had 1 amp flowing through this and 1 amp flowing through this, what's actually flowing through the fuse? Bingo, right? The cars they don't just come out of a portal. They all had to use this main road right here. So if there's an amp and an amp, that means up here there's 2. So what happens if the truck driver adds a 3rd and a 4th light? You got 4 lights. Each one of these lights is going to be 1 amp, right? How many amps are flowing through the fuse now? 4, exactly. What if the truck driver has 11 total bulbs and each of these have 1 amp? How many amps are flowing up here?
11.
Now the fuse is blown. See, if this is a 10 amp fuse, that will blow the fuse, right? So when you're adding a load in series, it's just further slowing down the traffic because there's only 1 lane. When you add a load in parallel, and the load is actually paralleled so it adds another lane, overall you're increasing the amps up here, and that's when you get in danger of, you know, potentially blowing the fuse. So that's the way to look at it from like the engineer of the circuit. The way that we troubleshoot these, to be quite honest with you, is like you'd look at it, let's say these are taillights. Let's make them headlights in this case. These are the headlights. You guys, if you walked up to a car and 1 headlight was working and 1 was not working, do you think it's the switch?
No.
See, you all know it. Like intuitively, you kind of understand. It's almost like if at your house you had the TV plugged into an outlet and you also had the microwave plugged into the same outlet. And the microwave works, but the TV doesn't work. You think that outlet doesn't have power? It doesn't make, you know, so you understand a little bit more than you expect. The way we troubleshoot the parallel circuit is first we just back up and we just say, are there any other loads that work? So if this one doesn't work and this one does work, this is what I can tell you. We must have 12 volts here. We must have ground here because this bulb is glowing, it's working. Now if it was, let's say, fans. If this fan didn't work and this fan did work, it's the same thing. We must have 12 volts here, we must have ground here because this fan is working. Whatever the load is, right? If the load is working, we know it has to have 12 volts and ground. That's what the load needs to function. So now if I were to break that down further, if this was working and I knew it had 12 volts, do I know it has 12 volts here? It has to, right? So the way we diagnose the parallel first is we look to see if there's other loads. And then let's just say these are headlights and neither of them worked. What would you suspect? 2 blown bulbs?
No, switch or fuse.
That's what I'd be thinking too. So first you think with your brain, right? And then if from there you can't, let's say like in your mind, yeah, probably fuse or switch, right? But when you actually go to confirm it, you can't start the treatment before you get the diagnosis. When you go to confirm it, right, we're probably basically going to troubleshoot this right here as like a kind of like a series circuit, right? And then we could troubleshoot this individually as a series circuit and this individually as a series circuit. So when we do the calculations for a parallel, it's different math applied because of Ohm's law. But when we troubleshoot it, essentially all we really do is break it into sections and troubleshoot it like this. So that's what I mean, this is your bread and butter right here. Like if you understand how to troubleshoot the circuit in line, like in a series, then you apply those same tests over here. After, of course, you've used your brain, because, you know, I'll show you a little bit of trade secret, okay? When I work on the car, and I'll paint it even a little bit more clear than I was going to. First off, when I work on a customer's car, I can charge them really whatever I want. So you guys are all very clear. But I should have a reason for charging that amount. I shouldn't just say, well, it's going to be $500 to troubleshoot that electrical system. Because it's like, at that point, you know, the customer could say like, you're ripping me off, and you should have kind of a good answer for why you're going to charge them, right? But technically, really in a court of law, if you were to say, I want $500 to troubleshoot this, and the customer, it's a free market here. If the customer were to say, I don't want to pay that, and you say, no problem, move on, move along, go find somebody else to do it. And especially right now, they may or may not. So I'm getting like more calls than ever. I don't even really have the time to work on people's stuff, but there's just not that many people who can really diagnose. You know, there's just fewer and fewer people, right? So you could charge whatever you want, okay? With that being said, now I'm going to change gears to, let's say you're working at the dealership for, you know, a major manufacturer. Let's say obviously Toyota is going to be my go-to, but we can make it different. Let's say it's Ford, okay? A four-letter word that starts with F. That's why I avoid Ford, but let's go with it. Ford, F-O-R-D. You're working for Ford, the car's under warranty. Do you know who pays the bill? Exactly. So when you're working for Ford, let me make it very clear, I doubt it. You're actually probably working for an auto group. So there's a Ford dealer locally, Tim Moran Ford. If you're working for Tim Moran Ford, you're actually working for the Tim Moran Auto Group. That's your employer. That's what it says in the paycheck. That's who signs the paycheck. That's who does your benefits. That's who does your retirement, which is probably like somewhat matched 401k, right? That's a dealership job. You do not work for Ford, period. Because it's not corporate owned Ford, right? So in your mind, you roll by the dealer and you're like, oh, that's Ford. Like, yeah, kinda. That's like a franchise. Tim Moran has an agreement with Ford. They put the Ford logo, but really actually Ford employees mostly working out of Detroit, and they've got some around Southern California and things like that, okay? So when the car's at the Ford dealer, Tim Moran Ford does service work and then sends Ford corporate in Detroit a bill. Make sense? Ford corporate says, oh, okay, yeah, we'll pay you. Boom. And the money goes, and it's real money, it's legit money. So some of the ways that we want to diagnose and troubleshoot are ways to justify our time, right? Because like not exactly to the customer, and technically you can charge the customer whatever you want, and it's a little fuzzy as to what you really have to justify. But when Ford is paying the bill, Ford's gonna be like, guess what? I'm not gonna pay you for 2 hours to diagnose that. I'm gonna pay you for 3/10 of an hour. And you're like, 3/10 of an hour? Like, what the heck even is that? Well, that's 8, 16, that's
20.
18 minutes? We did that math once, didn't we? 18 minutes? Is that right? 3/10 is 18 minutes. Yeah. So it's actually anywhere between 18 and like 20 minutes. You know, so basically they're saying, I'll give you 18 to 20 minutes. You think you can do that? Cool. Then take your 3/10 and move on. 0.3, sometimes we joke around, you'd be like, oh, you want diagnosis? It's 0.3 with an F. 0.3 means the car came in, they're like, oh, my headlight doesn't work. You as the technician go out there, first thing you got to do is verify, right? You turn the headlights on, the headlights work. You're not going to get paid anything by Ford. Ford's going to be like, you verified that they worked and that's it, ship the car. Make sense? Now, maybe the headlight doesn't work intermittently, in which case it's going to be like, well, you need to drive it, hit some bumps, maybe tap on it a little bit, whatever, get it to mess up. It's hard to even justify your time for that. Make sense? Because Ford is going to pay, but they're only going to pay as much as they need to pay. So sometimes the way we write or the way we explain what we did, you got to be a bit creative, okay? So, and I'm okay with saying this on record. If the car came in and this headlight worked and this headlight didn't work, I probably wouldn't write it up in that way. What I'd probably do is say, let's say this is the right headlight. The right headlight had 12.6 available volts. The left headlight, now wait a minute, how did I know it had 12.6 available volts?
Because you measured.
Did I though? And that's kind of what I'm saying. If you are doing everything exactly by the book, you measure it. But if this headlight was and 12.6 is probably a little too specific. So let's just say had good source voltage. If this headlight is glowing and it's bright and it's putting out enough lumens, don't I know that it has good available voltage to it? See, so in my writing to Ford, I'm gonna write it had good available voltage, but then this one I probably am gonna measure because it's not working, right? So the way that I look at this circuit, I'm using my brain to eliminate possibilities. If this one's bright, I'm good with the voltage all through all this. Make sense? I could get my meter out and I could measure these individual points, and that's great. And on the circuit board, I would absolutely do that. But in the car, you want to try to back probe that headlight switch, Yeah, you're gonna have to take your shoes off and put your feet around your head like this and be upside down with your headlight on and your meter and your back probing, and you just spent 10 minutes looking up the wiring diagram so you know which terminals, and it's terminal number 7 and 12, and the wire colors are black and red, and you're spending a lot of time, right? So if you can look at it and understand it and know this headlight being, I forgot which one was on. Let's say it was, this one was working and this one was not, right? Let's say that this headlight was on. I know that it has good available voltage. I don't necessarily have to go all crazy in there, you know what I'm saying? And do all these steps. That's better. That's better in automotive. The less actual probes and pokes you have to make, that's better. But you got to be able to write it in a way that's showing that you understand and showing you did diagnosis. So let's just say I wrote it like this. Verified left headlamp worked, right headlamp was in op. Found right headlamp was disconnected. How much time does that sound like it took?
2 to 3 minutes.
Yeah, like moments, like just instants. Cool. And they'd be like, oh, okay, great. Yeah, you'll get paid 0.1 maybe 0.0, nothing. You see what I'm saying? Mm-hmm. Now, in reality, what that may have looked like is this. You went out and got the car, you turned the lights on, you looked, okay, this one, I'm allergic to work. This one works, this one doesn't work. Then you open the hood. You know, a lot of times you can't even see that connector. You can't even see the sucker. You might have had to remove an air box. Sometimes you have to remove a battery. Sometimes you have to get at it, right? Did you write that? No, then it didn't happen. Make sense? So you gotta be very meticulous about what steps you performed to justify your time. Sometimes the people approving it, they think it's like the TV. Oh, the TV didn't work. So what'd you do? Looked right here and it was disconnected, and then you plugged it in. What'd that take? About a minute. Cars aren't like that. It's not real common that you can even see the connector. Cool? So then if you, let's say, had to move that air box back, and then you see right here, and you can see one of the connectors, and you go ahead and you start probing and taking measurements, right? You'd want to be able to document that, but I would probably do my measurements right here. Why wouldn't I do a measurement right here? Tell me why. Why wouldn't I do a measurement coming out of the switch? Because one works, okay? So again, that's the point. You have to justify why you're doing that test. Now let's say you went to Ford and you're like, I tested the voltage leaving the switch, and you're wanting to get paid for that, right? So you're saying my diagnosis took 2.0 hours, 2.1 hours, just for a real number. They're gonna be like, well, let me see your steps. Oh, you tested the switch. Wait a minute, why'd you test the switch? The customer concern is one headlight works and one headlight doesn't work. You really should have never been up there. Make sense? So it's going to be difficult. The customer will pay because the customer probably doesn't know. But when you're trying to get paid by the manufacturer will say, well, you know what? You're doing steps that don't even need to be done, okay? So that's more like why you need to really understand this, why you really need to understand this, and why first you try to use your brain. Using your brain doesn't take a lot of probing time and research time. You have to be able to understand this before you have any business trying to troubleshoot it. Otherwise, if I'm Ford, I'm gonna be like, it's clear you don't know anything about electrical. I'm not paying you to test here, here, and here, and here, and here. I will pay for you to test here though. So let's take, you were clocked onto the job 2.1 hours. Let's just start taking time off of that. And we'll be like, you know what? I think I'll pay you 0.3. Have a nice day. And you're like, what the heck? I did all these tests. This is a scam. And it's kind of like, yeah, but I'm just letting you know that's how automotive is. It's very hard to get paid for doing unnecessary diagnosis. Okay, so you all know. And then from there, how about this? Do you think I should test this ground right here? Why or why not? Between these 2 points. Why? Because one works, right? So see, on a parallel, you can eliminate a lot of your test points if one of the loads works. And that's why that's the first thing you gotta do. All right, so you think you understand series, right? You think you understand parallel? Then what's the difference over here? Series, parallel. Oh, the dimmer. Yeah, you know why this is what makes it a true series parallel, the dimmer. The dimmer is a load, and then it splits off. So this is a load in series, you can see that, right? And then it splits off and becomes two loads in parallel. So this is series, and then this is parallel. Isn't this series parallel? Kind of looks like it, but no, and the reason why is because there's no load in the series part. So all parallel circuits, generally speaking, are going to be like this because they come from one battery. So even if they were split most of the way, at the very beginning, it's coming from one battery. So it's still like a lot of the circuit, or at least some of the circuit's going to be in series, and then it's going to go to parallel. But it's not a series parallel because there's no load in the series section. That's what makes a series parallel series. Now, if it were me, to be really honest, I would spend very little time on this. Because if you want to troubleshoot a series parallel, you troubleshoot the series like a series, and you troubleshoot the parallel like a parallel. So if I teach you this, then I teach you this, pretty much you already know what's up with this. Make sense? But that's the difference. Now, in a car, are you going to see series parallel? Old cars, yes, because they literally had the dimmer. A new cars tend to have the dimmer, but it works different. The dimmer isn't a load in the series part. The dimmer is it's like its own individual load that's an input to the computer, and then the computer will just vary pulse width or duty cycle to the bulbs. Most of this is gone, to be quite honest with you. In fact, on a brand new car, I doubt that you'll even find one like this. But it's still something you need to know, and it's fairly easy to cover. So we'll cover it, but you'll already have most of it. All right, so let's go back with that series. Okay, and there's going to be some repetition, and that's normal because I noticed if you guys take a few days off, and then I ask you a question, you're kind of like, you lost something. Cool. So it's 2 steps forward, and then next week it might be 1 step back, right? But that's just how electrical is. You need some review. So here we go. I'm going to even draw on this one. And one of the actual next thing we really cover, we could do it in different order, but one of the next things we cover is tracing, circuit tracing. So we're gonna do a little circuit trace right now. If you guys know a series circuit, what voltage you think would be available right here? 12-ish. We'll go with 12 point. That is orange. I thought that was red, but if I'm gonna use orange, I might as well use the good orange. 12.6. Cool. What do you think about right here? Same. So you know what that means? I should trace this in the color of my choice, which in this case, we're going to call this red, okay? So this should all be positive. In another way to go about it, that should have power, right? So if I were to have a test light and I were to put my test light on there, it should glow, and it should glow. Make sense? If I were to have a power probe, it should go beep, beep, and on screen it should show 12.6, 12.6. If I were to use my meter, I'd take my black lead, I put it on ground, I take my red lead, and it should say 12.6 and it should say 12.6, right? Part of the reason that we get into tracing is because when you trace it and it's red, in your mind, you know, that should be about 12.6. Makes sense? So we trace it first so you know what the test results should be. So this is a preview on tracing, but this is the most simple circuit ever. They don't even have circuits this simple in the car. So we're just starting off very basic. Then it goes through this thing. What is this? Fuse. Okay. And what should it have coming out of the fuse? 12.6-ish. So we could basically trace this right here. You could even just go straight through. Cool. And then it goes to a switch. So if it has 12.6 right here, should it drop anything going through just a wire to the switch? Not really, yeah, so I agree. And then let's say that this switch is currently closed. What should it have coming out of the switch? 12.6-ish, yeah, and it might drop a little. So along the way, it's fine to lose little pennies, cool? So let's just say it even got to a 12.5. That doesn't matter. We're still drawing it as red, okay? You're still drawing it as red. And then what happens at the load? It should drop. How much should it drop? If it's 12.5 here, this should drop a 12.5. Okay? Or 6 or whatever. And it should be how much coming out? Zipperoonie. Okay? So we traced our circuit the way it should be if it's functioning correctly. What's the status of the switch when we're testing it? It's closed. Then close it. Then draw it closed and trace it. Now, if I were to go about doing my measurements, now you guys can see quite clearly, I would literally, let's say it was available voltage. I could put my black lead on ground. Anything that's red, it should be 12.6, 12.6, maybe 12.5, maybe 12.4. What if I were to get 10.0? 10.0 volts? No, why are we already dropping $2? We should drop pennies along the way. Right, 12.6, 12.5, 12.4, 12.3, not 10, not 9, not 8, definitely not 6, right? We're not going the right direction. So anywhere in red, right, if you were to have your meter and you were to have this diagram, you'd be like, you can process very quickly, especially when you're under the gun and there's a customer waiting and you're worried about how much you're going to get paid, right? I'm trying to pull you to a high level where you can function in that environment. The go-to, first off, you can start taking ashwagandha gummies, okay? But really, probably the thing is, follow the protocol. Trace the circuit out. So you're not under here being like, all right, I'm going to probe here. Now, what should it have there, right? Get this, trace it out, and then everywhere that's red, 12, 12, 12, 12, 12, 12. You don't have to rethink it, right? Trace it first, so then when you're under the dash, all contorted, getting yelled at, thinking I should have had the ashwagandha gummies, you can just fall back on, if it's red, it's supposed to be source voltage-ish. Cool, boom. If I measure right here and it's 10, I know there's something wrong. Now if it's black, and sometimes we'll do the ground in green, so I don't know, you pick. The green just makes it a little easier to see that it's not just the ink. Either way, what should we have on the green? Zero-ish, 0, 0, 0, 0, 0, 0, 0, right? So if you trace it, you should be able to punch in you should be able to know quickly if it's a good measurement or bad measurement. Realistically, you're not going to measure this when it's functioning, okay? Why? Back up. How would I know this circuit is functioning? How do you test it when you get in the car without your tools? The headlight's on. Boom, this bulb. Whatever this bulb is working. No test performed. Make sense? That's why I remember the first step in diagnosis, verify the concern. If the customer says my headlight doesn't work and the headlight works, you can test everything you want. You could probe every inch of that wire. The bulb's already on. You're wasting your time. And in fact, I'm not going to pay you because I'm Ford and I'm not going to pay. It was good we picked Ford because I could trash talk Ford for like the next hour. Okay, but I'm not going to pay you because the bulb was on. I already know that all the voltage measurements can be good. The only way that we're going to actually test this is if the bulb is not on. You'd trace it like this. Then you would perform measurements, and if the bulb is not on, you're going to find something wrong. So let me give you the most simple, yet a little complicated example. My black lead's here, 12.6, 12.6, 12.6, 12.6, 0. 12.6, 0, 12.6, 0, but the bulb doesn't work. What wrong? Bad bulb. Bingo, done. That's how simple it would be. Now, matter of fact, the way that I would test this, I'll tell you straight up. I'd go like this. 12.60, done. I wouldn't have wasted any of my time back here. Sometimes I start at the middle, sometimes I start at the load. Depends on the job, right? But if I have 12.6 and I have 0, well, that means that the bulb has everything it needs to do the job, but it's not doing the job. Get rid of it. That's what I'm saying. Gotta go. Now, if I test the bulb and I see 0, am I going to get a new bulb and plug it in there expecting it to fix anything? No. Because it doesn't have what it needs, right? So then if I back up and I see 0 here, then if I back up and I see 12 here and 0 here and 12 here, then something's up with the switch. Exactly. So it's not complicated, but it's helpful if you know, hey, everything here that's orange, it should be 12. And if something's reading 0 on a wire that I previously highlighted in orange, something's up. And basically then you're just looking for where it goes from 12 to 0. Or it might be 12 to 6, right? 12 to 0 would be like an open. 12 volts to 6 volts would be like a high resistance. Makes sense. But either way, you're still knowing what component's bad. It could be the fuse, it could be the wire, it could be the switch, it could be the male, female terminals, right? These are the things that we're nailing down. So if you can follow that, basically, you're ready to troubleshoot on the car, except we got to do back probing and stuff. Now, again, as a little somewhat review, if we have 2 bulbs in series, and this source voltage is a 12.6. Remember, I've explained it many times. That's like the parents are handing down $12 of an allowance that has to be shared across, shared between 2 twins that are of equal size and strength. How much money does each twin get? 6 and 6. Okay. Remember that? And we did a lot of complicated math. What if this one was a 4 ohm and this one was an 8 ohm? Because this is double the ohms, it's going to consume double the voltage. So I believe we figured that one out as this one's going to drop 8 volts and this one's going to drop 4 volts, right? If it was a 12.0. Cool. So we did this calculation several times. Is it kind of ringing a bell to you? Like, it's almost like, let's say, 2 brothers, we'll make it brothers. This brother is 8 years old, and this brother's 4 years old. This brother weighs 80 pounds, and this brother weighs 40 pounds. Trust me when I tell you, this brother's going to take about $8. It's going to take double the amount of this brother. It's just proportional. Like, that's why some of the science and the natural sciences, you may say, like, they make sense. It's never like, well, I don't know, it depends on how this bulb feels that day. Like, no, the bulb is 8 ohms and this one is 4. It's going to take double. It's going to take double today, tomorrow. It's going to take double. There's no free will right here. There's just Ohm's law and how it's applied, right? So you could predict it, boom. But this isn't what customers have us do. You know what the customer has us do? Let's make this bulb is now invisible, okay? You remember, this bulb was the 8 ohm bulb, wasn't it? What if this bulb wasn't a bulb at all? What if this bulb was 8 ohms worth of corrosion? What would happen to this bulb? It would be dim because this bulb up here is 4 ohms, which means it's going to take 4 volts. And this corrosion that's 8 ohms is going to take 8 volts. This bulb is going to be extremely dim. The problem is you're seeing the bulb, you're seeing the electrical theory. If it's corrosion, you can't necessarily see that. You got to go track that down. Right? So if we were to measure this, I put my ground right here and I could say, oh yeah, 12 volts. Let's trace it out. What should we have? 12, should 12 go to the switch? I mean, through the fuse, through the switch, right?
Stop.
And where else?
Down to the bulb.
To the bulb. Now, I'm going to pause on that. What should we have right here?
0.
Exactly, so we could draw that. And now this is the thing. On this circuit, we would have an in-between voltage right here. By the way, that's why it's drawn in a different color. It's blue. But if this bulb was not a bulb at all and it was corrosion, we should actually have ground going all the way up to here, at which point we do our diagnosis like this. Put your lead here. 12 volts, 12 volts, 12 volts, 12 volts. What should I have right here? 0. I should have 0 because this bulb is corrosion. I should have 0, but if I measure voltage on the ground, I'm giving you like kind of a a professional tip here. If I measure that there's still positive voltage, like in this case, there's 8 volts on the ground, I already got it diagnosed. If there's positive voltage left over on the ground, you're like, it's a short to power. No, it isn't. It's just there's high resistance in the ground. There's extra resistance. The fact that there's still $8 left over means this little brother only took 4 volts, not because it was nice. It's not like, well, I care about humanity. It's like, because I know that there's somebody with double my might makes right, okay? I know that there's someone with double my weight and age down here, so I only took 4 simply because I know that there's 8 down there. Where is it at? Well, you knew it was down here because there was 8 volts left over on the ground. Make sense? So then you could test here again, and it's still 8, and then if you test right here and it's 0, you know the problem is right here. It just doesn't look like a bulb. It looks like chalky green disease or something because somebody probed a wire. Make sense? That's how you troubleshoot it. All right. Now let's apply resistance. If you didn't want to do available voltage, that's fine. You could do resistance, and you could disconnect the positive, right, and close the switch, and you could be like, measure the resistance of this wire, measure the resistance of the fuse. What should a wire measure in ohms? Come on, give it to me. Not much, yeah, 0-ish. What should a fuse measure in ohms? 0-ish. What should a switch measure in ohms? 0-ish. What should another wire measure in ohms? 0-ish. The bulb, do you remember what I said the resistance was? 4 ohms. What should this wire, because remember this bulb's not here. What should this wire measure in ohms? 0-ish, but if it measures 8 ohms, you're like, oh dang, something's up with that wire. Makes sense? The wire shouldn't be measuring 8 ohms. That was 2 different ways to test the same fault. You can prove it's wrong this way, you can prove it's wrong that way. Voltage would be the preferred, okay, but ohms can do it too. Okay, so here we go. Let's break these down. Because we were just talking about available voltage a lot. And available voltage is fine, but there's a law here. The sum of all the voltage drops should equal the source voltage. So in this diagram right here, this actually, can you tell how many loads are in this diagram? In this schematic, if you will? 1 here and 1 here. Exactly. So this one's a good example. The sum of all the voltage drops equal the load. So if I were to take my meter and do voltage drop, okay, that's what this is. This is voltage drop. How much did I drop across the fuse?
0.2.
On this one.
0.1.
Yep, 0.1. How much across the switch?
0.1.
0.1. Okay, those count. Those do take away from the $12.60 that the parents passed down. Or it might even be, well, whatever, we'll do the math. What am I dropping across this dimmer?
4.7.
That's interesting. Okay, and then how about across the bulb itself?
7.4.
Yeah, and then how about on the ground?
0.1.
Let's do the math on that. Anybody figure that out? Ready? I'm going to tell you, whatever that sum is going to be the source voltage, okay? So 12 even, maybe that could be. Okay, 1, 2, it'd be 9, 10, 0, I agree. Carry the 1, right? 5 plus 7 is 12.0. So if you had a 12.0 volt source, that'd be a 12.0 volt battery. All of these will always, always, always equal 12.0. What if your battery source was 12.5? All of these will always equal 12.5. So if that's true, and let's just pretend this dimmer wasn't here, okay? Let's make this dimmer gone. If that's true, and I come down here and in one foul swoop I use voltage drop like we were doing, right? If I go down here and this bulb is dropping 7 volts, is this circuit good or bad?
Bad.
Exactly. Like, why would the bulb only be dropping 7? It's supposed to drop about 12-ish, the source voltage. It should drop 12.0 in this case.
Something's about to explode.
More like there's a parasite, right?
It's going somewhere that's not supposed
Like a tapeworm. Like a tapeworm.
to. Taking my friends.
If you're eating calories and you're like, I put 12 calories in there, that wouldn't be a lot. I put 1,200 calories in there, and then you measure the actual body only consumed 700 of the 1,200. You're like, that's a tapeworm. It's a big tapeworm.
Maybe I can take it.
You know, that's one, well, no comment.
I'm going to go back to the 1800s.
If you do that, just keep it to yourself. Don't you be sharing that, right? But it's kind of the same idea. This dimmer, first off, in this actual circuit, the dimmer is an engineered part of the circuit, so that way we can brighten and dim the bulb. Why would we want to do that? To set the mood. Or if you're driving on the freeway and it's late at night, maybe you don't want the super bright lights because it affects your ability to see deer jumping out or something, right? So we design it so this can dim your instrument panel lights. It's not to dim your headlights. Headlights are not supposed to have those be dim. Okay, but if you measure boom right here, you should be able to tell what's a good circuit, what's a bad circuit. Now, if we were to measure here and get 7 volts and you're like, that's not good, well, then you can do this diagnosis in a few different ways. You could measure individual components, right? And maybe the next step you do is you measure the ground, and the ground is 0.1 volts. You measure right here and it's 0.1 volts. And then you measure between this connector and this connector and it's 4.7 volts. And you're like, I should not be doing a voltage drop of 4.7 volts across a wire. You're never supposed to be dropping 4.7 volts across wire. You're supposed to be dropping like a 0.1 or maybe even less. Make sense? So you could do your diagnosis like that. The other way that we could do this is kind of summarizing available voltage. I could, once again, take my negative lead, hang it down at the metal terminal, the negative terminal of the battery, a good ground, a bare metal surface, and I could check the voltage available. So at the source, what did we have? 12.0 up there, right? So what should I have here on my meter? Right here with my leads just like this. What should it read? 12.0. What should I read after the switch? 12.0. 12.0, but if we're following, we're dropping a 0.1 volts, what are we going to read? 12.9. What about after before the switch? Still 12.9. See, so they're not having the wire drop anything, but they are saying the switch might drop a 0.1, so what would we be down to here? 12.8. And then if right here I were to measure the wire and I were to drop a 4.7, where would I be at?
8.1.
4.7. 8 minus 7, 1. 12 minus 4.
No, it's 11.8, not 12.8.
Oh, corrective.
11.9.
And going into it, it's 12.8. So what we're 7.1. Okay. Okay, he is. He definitely, that's true. You need to, in any electrical class, you're hired. Okay, so coming out of this, we should have 7.1. Does everybody understand how we did that? If we start with 12.8 right here, or I'm sorry, I messed all that up.
11.9,
Yeah, I was all sorts of got ahead of myself. It's adding voltage. Resistance can never add voltage. I was confused. Oh my gosh, that's how I lost my hair. I got so stressed out. The kids made fun of me. They called me so dumb. They're like, okay, anyway. So we went 12, 11.9, 11.8, 7.1. What do you think about that drop? We went from 11.8 to 7.1. That's on a wire. That'd be like, why is that wire consuming so much voltage? Tell it back to me. Why would a wire consume that much voltage?
Corrosion.
There's resistance inside, maybe due to corrosion, maybe due to you got the male, female, and there's like, it's just barely touching. You guys ever had a car where it won't start and you go wiggle the battery terminals and it starts? That's corrosion. That's a bad connection. That's like, you might have temporarily fixed it by getting a fresh fresh section of metal touching a clean section of metal, right? So that would be resistance. You drop voltage right there. Then if we were to have 7.1 here, it'd be 7.1 going in. If it was 7.1 right here,
0.1 L.
exactly, this bulb should drop to 0.1. Now the reason I knew that was because we did the voltage drop earlier. So if you look at these numbers, your voltage drops like this will always equal the source voltage, but also if you do available voltage with your ground lead down here and your meter leads all stretched out, you're going to do 12 to 11.9. How much did it drop? 0.1, right? Well, that's what your voltage drop said. It's the same thing, it's just a different way to do it. Rather than measuring the voltage drop like this, you can measure how much you had 12 volts and now you have 11.9, so you know you dropped 0.1. Okay? Whereas measuring it like this is just telling you the difference between red and black. That tells you on the meter how much it dropped, but it doesn't necessarily tell you how much is available. Make sense? It depends on what you want. If you want to know how much is available, measure how much is available like this. If you want to measure voltage drops specifically between the red and the black, then measure like this. It's up to you. It's two different tools for you to diagnose the car.
So, if you're testing for ground, you can't you can't put the ground on anywhere on the chassis. It has to be from the circuit.
No, it actually can be. So I'll bite on that. So right here, you see this is just a generic ground symbol. This ground symbol would be like, let's say you're testing inside the car. You know where your seat belt bolts up. Sometimes you can access that. Sometimes where the seats bolt to the floor and the unibody, you can use those. Anywhere that you can find metal that's connected into the whole chassis, that's good. But the reason I'd like to bite is, let's just say I'm working near the blower motor and I open the glove compartment. Right there, sometimes you have this little striker that's for your glove compartment door latch, and it's a little piece of metal, and you're like, oh, bare metal, it's shiny. And you clip your lead on there. That bare metal may be bolted to plastic only. That would not be a good ground at all. So you have to be a little careful about where you put your lead. If it's a piece of metal that's floating in the air, or if it's a piece of metal that's literally just bolted to plastic, that's not grounded. So you can put it anywhere on the ground, because ultimately this circuit, if we were to draw it out completely, and the wiring diagrams don't show you every aspect of the circuit because it'd be 100 pages every time, you'd actually see it go to chassis, you'd see the frame right here, you'd see a whole bunch of things go into ground, and then you'd see the frame over here go into the black battery cable that goes to your negative battery terminal. So you could test it here, you could test it here, you could test it here, here, because it should all be good. Makes sense? It should all be grounded. Now, if you get a measurement of, let's say, 3 volts right here, that tells you there's a problem in the ground because you shouldn't have 3 volts left over. That would mean 3 volts left over is being consumed by corrosion, unwanted resistance in the ground circuit somewhere, maybe even right at the negative terminal. If your negative terminal was dirty, you'd have leftover voltage on every ground circuit on the whole car. Every single ground circuit would have voltage left over. So sometimes the way that, like a lot of the untrained people will be like, oh, you have an electrical problem, you always check your battery first. And there's a little bit of wisdom there. There is some. It's like, yeah, because your battery can cause all sorts of stuff. But if I have 1 dim bulb and 100 regular bulbs, trust me, it ain't gonna be the battery. Make sense? So you gotta go about it in a way where you really understand. Don't just become a robot where it's like, we need to check your battery first before we do anything. It's like, hey dude, I got 1 headlight out and 1 headlight working. Leave the negative battery terminal alone. That's not it. Cool. So here was that breakdown of the available voltage, just showing the meter, the positive, and you could start at 12, 12.9, 11.8, sorry, 12, 11.9. Because I'm thinking of 12.6. 12 volts even, My second measurement is always 12 point something because it never starts at 12 volts even. 12.0, 11.9, 11.8. These made sense. We're just paying, pennies to use the road, to use the bridge, to whatever. And then 7.1, you're like, what?
Just got mugged.
That's what happened. It was like, here I went to use this little back road. I had $11.80 in my pocket. By the time I got out of the back road, I have it said $7.10. Somebody robbed me. That means that there's a problem in here. Because I was planning to pay nearly $12 to this bulb right here. $11.70 or 80 cents, to this bulb. I've only got $7 left for this bulb. The bulb's like, what happened to the rest of the money? And you're like, I got robbed right here in that dark alley. You got to go in the dark alley and find the unwanted resistance, maybe corrosion or similar.
Where's the money, Lebowski?
Yeah, I don't know who Lebowski is, but there you go. How you doing? Okay, so this should make pretty good sense to you. One of the ways that we can help it, that we're going to be doing after a break, is going to be trace all this, right? This should all be red, 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 red. Now, this has a load on purpose, but let's just say this load is unwanted. We should actually draw red all the way down to here. And you'd be like, what's the available voltage right there? You'd be like, 7 volts? What? Where'd the money go? Gronkowski or whatever? Gronkowski, where's the money? And then you're like, right here. Oh, I lost it right here. So you know the problem's here. So we're hunting down the perpetrators, if you will. Cool. And that's so you should be pretty rocking on available voltage and voltage drop. Okay. 2 different tools. Which one do you want to use? It depends on the situation. I'd say starting out, if it were me, I'd probably do the available voltage. I think the available voltage is a little more easy to understand in your mind because you're like, oh, I had 12, 11.9, 11.8, right? And you're following the whole thing. Now this one's just how we measure series. Current in a series circuit. You have to, do you see what we did here? We opened the circuit up. Now if I want to measure series on this circuit, where should I measure it? Should I do it here? 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 Actually, it can be done anywhere. Think about it as a 1-lane road. If it's a 1-lane road and you want to know how many cars are going by per minute, well, you can measure it anywhere on the road. It's all the same. If a car got on here, there's nowhere else for it to go. It's going to come out the other side. Make sense? It's kind of like, if you're on a canyon road and there's only one way in and one way out, and you pass a police officer oncoming going too fast, they're just going to call up ahead and be like, hey, this guy's going to come out the other end, right? These electrons have nowhere else to go. There's only one path because it's series. Cool, but what should I definitely not do? I could measure current like this without disconnecting it. What did I just do if I measure current like this? I'm even going to draw it. I did blow the fuse, and you guys caught that from last week. Very good. But I want you to understand why you blew the fuse. Are you ready? If I put my meter like this, I'm basically tapping in, coming over. This is going to be my meter right here. Okay, the power is going to go in there. The ground is going to come out the common and go over here. Doesn't it look like a parallel? It is a parallel. But what's the resistance of your meter when you have the lead in the big A and it on amps? I'll give you a clue. 0 ohms. So now visualize this. You got electrons coming down and they're like, go through it. No. Electrons like water, which is like some of you. They take the path of least resistance. And they're like, oh, no, it's way easier over here. How many can we take? Everybody, go now. Send it. So if you were to do the Ohm's law on this, tell me the resistance in these. You guys remember Ohm's law, right? The V, the A, the R, which you could also do as an ohm, right? So the voltage is how much? Do you remember?
12.
12. Now this, we know the resistance of the meter, okay? So you would technically you could technically do this as a parallel and do the math with the 1 over or whatever. But I'm just gonna say, just focus on this. If they can take this path, and let's just say the dimmer's not there, I forgot about the dimmer. If the dimmer's not there and it can go through your meter, is it fair to say that there's like basically no ohms right there? Let's even make your meter have like 0.1 ohms just to do the math. If your resistance is 0.1, how do we come up with your amps? 12 divided by 0.1. I know you can figure it out, but we're gonna do it. 12 divided by, what was the number? Am I right? How many amps do you have? 120. How do you think that your meter like that?
Not at all.
Makes sense? So now you really understand why you blow your fuse is because your meter has basically no internal resistance, which means the electrons will flow as fast as they possibly can. There's no stalled car. There's nothing slowing it down, right? And then you're going to have too many amps, you're going to blow your fuse.
What
Okay.
if they put a resistor in there? Will it mess up the readings?
I like that. Think about that. When you measure the amps, you want to be non-intrusive. You want to be like, measure them how they're actually flowing. So if you add a resistor, you just messed it up. You just totally blew out your reading. So now you understand it pretty well, I think. Now, how often are you going to measure amps? Amps could be used for diagnosis as well, but to be honest, like voltage, available voltage and voltage drop is the go-to. Once in a while, resistance, yes. Once in a great while, you may want to measure amps because you have a fuse blowing. Makes sense. It's not something we do real common. There's another one. There's a couple more examples though. A fuel pump that's getting old and starting to wear, they can draw more amps, so you might measure amps. So it's like you do this, but not all that often. But there are times where you will do it. Okay, now remember how we measure resistance, right? Disconnect the component from the circuit and measure the component, period. So like this dimmer, for example, 16 ohms. If you wanted to test the dimmer, you'd actually put it on resistance and you could move the little knob. And if you wanted the lights to be really bright, what would the resistance be of the dimmer? Think about that.
0.
Low resistance at least. Yeah, low resistance. And if you wanted the lights to be dim, what would it be? High, exactly. Because remember, it's a series circuit. It might even be a series parallel. But if this voltage, if this resistance is more, it's going to consume more volts, which leaves less for your bulbs, so they're dimmer. If you turn this resistance down, it's going to consume less, which leaves more for your bulbs and they're brighter. That's the design of the circuit. Cool. And so let's break this one down. In fact, yeah, let's go ahead and we'll take a moment and we'll build these circuits. So you guys are going to build each one of these circuits. Tim will do a pause, and you guys get to drag those things out, build a couple circuits. All right, let's talk through the activity here. This is the diagram. So it goes from 12 volts to a fuse, yes, through the fuse to a lamp like this, through the lamp to the ground like this. Nice switch, through the switch, I should say, through the lamp to the switch, and then from the switch to ground. So essentially this is a ground side control, you may say. With a ground side control, we could do things a little bit different, but normally if it's a customer car and we have a problem, we're going to test it with the switch closed, because that's the circuit's active, right? So yes, the diagram says open, but let's close it. From there, let's take a look at your voltage predictions. Point A is this point. Where's that on the board?
Oh.
Right there. So when we're saying predict the voltage, it's, if you look, it's the available voltage on predict. Predict the available voltage. How much should we have?
12.6.
That's right, because we started with 12.6 or whatever the actual voltage is. We shouldn't drop anything on a wire. It should be that. How about on test point B?
12.5. Let's say just
Because we might drop a little, some pennies, right? Because it's normal to drop a little tiny amount. We should not be dropping a big amount. I agree. And then what about going into the bulb? That'd be test point C.
12.4.
Yep, okay.
12.5.
Okay, and then, so that's going into the bulb. What about after the bulb? Here.
So be point D. 0.2.
Exactly. So this number is a yes. So this is your closed switch. I agree. Why should it drop so much going through the bulb?
Because it's a load.
Right, the bulb is the load. So we anticipate it to drop almost the whole source. And then after that, testing, at point F, actually we should test going into the switch at point E. You expect 0.2, about the same. I would agree. Going through the switch, we should get about 0.2 or 0.1 or so. And then we should have full zero right here. So your predictions are good. I agree with that. If you can't do these predictions, you can't fix the car. If you can't predict what's good or bad, you can't do it. When we troubleshoot, you get a diagram like this. You don't get a test point A, it should be 12. It just gives you the diagram. You have to come up with your predicted voltages. If you can't do that, we're done. You got to fix that before you do the actual. Now we did one more for fun. If we were to leave the switch open like this, we get different numbers. So would you agree? What about point A?
12.6.
12. Yeah, let's call it even 12 for simple. 12. What about at point B?
12.5.
What about at point C?
4.
What about at point D?
12.4.
Isn't that crazy? So if the switch is open, the 12 volts goes through the load. The 12 volts should go all the way to E. And you agreed on your open numbers. That was true. Now the way that tricks a lot of people. The reason that is, if you think about it, the switch is open. This has much more resistance than the bulb. So therefore it would go through the bulb and be waiting right there. So you think of it like stalled car, right? If this is a load, that's like a stalled car. But if ahead of the stalled car, there's a toll bridge and the bridge is up, right? The cars are going to go around the stalled car and they're going to be waiting right there. Your 12.6 will be right at that point. But see, the bridge is up, so they can't cross. All the 12 volts will go right to there, and then it would be zero down here because nothing is going through. Your amps would obviously be zero. Now, if we close it, what happens is all these cars that were after the stalled car get to go over the bridge. Boom, they're gone. So all this drops to zero, and all this is going to be backed up with 12 behind the stalled car was kind of the way that I like to think about it. So you gave me good predictions for closed switch and good predictions for open. That was pretty good. And then your measurements, run through, show me your measurements. We'll go through and we'll do the available voltage. You guys remember how to do that?
Yeah.
Okay, run it. And you can do it pretty quick because we already, we're getting the hang of this. We've done this a couple times now.
So available voltage over here.
12, good. Good. 12-ish, good. The wire's good. Still 12-ish, that tells me the fuse is good. Still 12-ish, that tells me the wire's good. Going through the load, it drops to basically zero. What do we got here? It changed over to millivolts, right? So you have 17.5 millivolts, that's 0.0174. Right, so it's dropping almost the whole thing on the bulb, right? And then after we're zero-ish, and then you get slightly closer to zero after the switch. So this is a good functioning circuit. What if I were to open this? Run through the available voltage. What do you think? All the way from the beginning.
So be all the way through over here.
12. 12.
Well,
Show me. 12 is true after the bulb. 12 volts. Is the bulb good or bad? It's good. It's just we're not testing it with it active. So what about here?
12.5.
12 still? Yep. What about here?
Zero.
Why?
It should be like,
Because
does
it's
it
close.
drop?
Because the switch is open switch. Yeah, the circuit is open. Exactly. Yeah, so you guys nailed it. Now, I'm going to say, let's pause because I want to do something. All right, so won't tell the story, but I turn the switch on, the circuit doesn't work. So let's run through the available voltage so we can do a fairly quick diagnosis. We predict 12 volts. We got 12 volts. Next test point, we predict 12 volts.
Yes.
We got 12 volts. What do you predict for here?
0.
Well, it shouldn't be 0.
12
What
volts.
should it be?
12 volts.
12, but you have 0. So go back to that one. You have 12. Go back to this one. You have 0. So how much did it just drop right there?
12
Sorry.
volts.
Why is it dropping 12 volts on a fuse? It shouldn't drop 12 volts on a fuse, should it?
There's resistance.
No. Yeah, a lot. Probably even a full open. Now let's test it one other way. Do you remember how to test voltage drop?
Yeah.
Voltage drop this wire. Show me if you know. Voltage drop that wire. What are you dropping on that wire? Point, just nothing, exactly. Now voltage drop the fuse. How much should you voltage drop?
0.
Yeah.
But yet you're dropping 12 volts right here, see? So you just did 2 tests to confirm there's an open somewhere between this and this. Here's one more test we'll do. Test the resistance of the fuse in its circuit. We got to disconnect the circuit, right? We'll disconnect it in both spots. Change it over to resistance. How much resistance should you have?
Open.
How much should you have?
I don't know. No, so much? Like 0.1.
You should have nothing, but you have. You just showed me in available voltage this fuse was bad, in voltage drop this fuse was bad, in resistance this fuse was bad, and this is the type of work we do. Now, we'll show you one more way. You pull that, I think I just got it. If you don't know what you're doing, this is how you test it. That fuse is blown, but you can't always see, you can't always rely on that. This is the good fuse. Okay, you can see it's actually, this one's kind of dark. Yeah, a little too dark to see. But that's why you don't want to really rely on just looking through the plastic. The way you just tested it right there was good troubleshooting. All right, pretty good. So we'll move on to the next part. All right, series circuit. If you want to measure the amperage, you can follow all the steps. But if you think about it, it's a series circuit. So your amps should be the same anywhere. Go ahead and show me amps reading, like up at maybe around point A. So we're changing this to amps. You move the lead, so now it's to the fuse 10 amps. Now how do you do it? Good. Disconnect the circuit. Very good. Your red lead will go on the most positive. Your black lead will go in a way where now the electrons leaving the source have to go through your meter, come out your meter, and still go through the circuit. Cool? And we're getting a half amp, 0.523. All right, now let's put the circuit together and let's measure it down here on what we'd say the ground side is and see if it's any different.
20.
How about here? We'll do right there. That's one way. This way makes a little bit more sense to me just so I'm less confused. So now you still see it's leaving the source, it's going through the fuse, and if you trace it, it goes here, through the meter, back out your meter, and continues, right? So that's what we mean when we're putting it in series. And look, you got more or less the same number. The number is going to be the same all the way through. It's not like voltage where the voltage is confused. The amperage in a series is going to be the same, because there's only one lane, and the cars can only go so fast in the one lane. Okay, so that one's good. All right, so we'll build a new circuit. Similar circuit, except we're going to add 2 loads, and the loads are in series. All right, check back in. They got predictions. Here's your diagram. So you guys predicted A, 12.6, 12.5, 12.4. So basically good 12 volts, 12 volts, 12 volts. The critical one is D. So what did you think for D? About 6.4? I mean, that's probably pretty accurate. 6.4, and then to E it shouldn't drop much, right? And then F, what do you think?
0.3.
Your predictions, I think, are going to be really good. Show me the measurements. Let's see how you do. All right, so here we go. Now, once again, we're doing available voltage. So we got the meter lead in the ground. Okay. At point A, oh, we got to change it back over. Forgot we were measuring amps, huh? Get it back onto voltage. There we go. Your source is 12.05. Cool? 12.05. So what do you think about, let's go for B. 12.04. Yes, that makes sense. It dropped a tenth across the fuse. C? 12.04, you're still accurate. Now this is a big one. How much did we think it was going to drop?
6.
About 6. So we'll have about 6 left over. So we'll go right there. Yeah, I mean, you're pretty close. 590. So it dropped, about 6. Coming in here, we should still have about 590.
Yeah.
Coming out, how much? How much? Almost zero-ish.
0.2.
Yeah, and we've got 6 millivolts, so that's 0.006. So you're basically 0 right there. And then 0, and then really 0. So guess what? It's really about the same. It's the same type of measurement. It's just this is going to consume 6 and this is going to consume 6. Make sense? Now you're going to do another one with the third bulb. We're actually going to skip that because if this one is 6 and this one is 6 and you had 3 bulbs, 2, 2, and 2 would only equal 6. So to be 12, 4, 4, and 4 is correct. And then if you were to do 8 bulbs and 12 bulbs and you could do, it's the same test. The one I'm going to have you jump to is actually not a bulb. You'll see one where it's adding a resistor in here. Did you see that? All right, so I want this circuit, right? In fact, do it with 2 lamps, right? We don't really need 3 lamps. Do it with 2 lamps and that resistor. And that's going to really show you a good lesson.
This one?
All right, so when you build this, right, you could again predict your voltages. So we're just going to walk through this. You predict 12 going through, 12, right? 12 to here, because when we trace it, there's no load there, so it shouldn't drop anything. When you get to here, it should drop something, right?
6.
You'd think it would drop 6, and then you'd think this one would drop 6, but what you didn't account for is this. So this is an added load, but it's a load that doesn't give you light. It doesn't really do work for you. So we're going to make this the unwanted resistance, okay? So the reason I had you do 2 bulbs was because let's look at this circuit. If you were coming in here, you'd have 12, right? 12 right here. You drop to 6. Then you drop to 0. If you had a big, excessive, unwanted, dirty, nasty resistance right here, you'd get exactly what we got. The bulbs don't work. Make sense? So let's do a available voltage measurement all the way through. And then we'll describe this as a connection. I know it's a resistor, but we'll describe it as a connection to make it applicable. Here we go. Let me pull this around so we can see the wires more clean. All right, so tell me, what do you expect? You got 12, yep. Go ahead through the fuse. Yeah, 12.5. After the fuse, 12.4 probably. 12.5, doing better now. Going in. 12.5. How much coming out? Wait a minute. How much do you think? It's going to drop.
I'll say
About
0.
5, 6.
We want it to drop about 6. Go ahead and do it.
I'll say 0.
We still have 11.7. So this thing barely took $1. Why is it only taking $1?
Because someone else bigger. is
That's
waiting for it.
exactly. So that's how I understand it. If you got 2 twins and they're like, hey, mom and dad, give us allowance. We're expecting 12. You get 6 and I get 6. If there's a really big, strong brother that you don't know about in the second family, you get $1, you get $1. That sucker's going to get how much?
10.
Like about 10. Let's see if that comes true.
11.7.
Coming in about the same. Yep, and then going out.
11.5.
Oh, that one took barely anything. Okay. Going into that big unwanted, accidental, bad connection resistor. How much coming out?
Yeah.
This thing took 1150 and left these with just pennies. All right, so here's, and you measured that, right? And so here's really the lesson. If this resistor is a bad connection, it'll make the bulbs not work. How do you track it down? See how much is available, right? There's 12 coming in, there's 12 going out. There's 12 coming in, there's 12 going out. These are consuming nothing. These consumed a little, right? So there was 12 coming in, 1175 coming out, 1175 coming in, 1150 coming out, and this sucker is getting 1150. This is consuming all your voltage, right? So normally it doesn't look like a resistor. Normally it's invisible. The customer comes in, their lights don't work. You start testing and you're like, why am I dropping so many volts on this part? So if I were to have covered this up, ready? Pull that red lead. If I were to have covered this up, now I want you to look at this circuit. See that green wire going around? Let's pretend it's just a wire. Now go ahead and measure that available voltage at that point right there. So we've got 11.5. Now measure it on the other end of the wire as if it's in the car. You went from 11.5 to like basically 0 on a wire. Something's wrong with that wire.
There's too much resistance.
Exactly. It's or something. So this is more how you work on the car. You can't see everything. Like if you look, that corrosion could be in that quarter panel or something. So you got to be able to test it. You might need to test it here and then test it here. You might not be able to test it where it's behind that interior trim, right? So this little clipboard actually makes it work pretty well. So that one is helping you to tie it to actually fixing the customer's problem, right? So you guys, that was a pretty easy test, right, to do those. So if you were to look at this one real simply, you'd expect 12 volts, correct? You'd expect 12 volts, correct? You'd expect 12 volts. What would you expect here?
0.
It better not still have 12 after it drops the load, assuming the switch is closed, if you're being smart with me. So when we test the car, remember we close the switch, it should drop all the voltage on the load. That's the main summary of what you guys did. Then you could do it with 2 bulbs. Because it's in series, you should have 12, 12, 12, how much?
About 6.
About 6. And then how much?
0.
Basically nothing. We should never carry over much to go through the switch. The switch should not consume much. We shouldn't be paying a big toll to use this little bridge right here. We should be spending all our money on the loads. And then you could do it in 3. And if it's going to be 3, you should have 12. And then how much should you drop here? Probably 4, 4, and 4, wouldn't you say? Right? Yeah. So you should go from 12 to 8 to 4 to 0. That's the series application. Now this one is where it gets interesting. And we did a quick experiment while you guys were working on your stuff. And the reason that this one's interesting is you'd look at this, and if there's 3 bulbs, how much voltage should you drop on the 3 of them?
4.
But what about that? See, that's the problem. This resistor, it's equivalent to unwanted, undesired, bad resistance. So let's just say that this resistor is here. What's really going to happen is it's not going to split up between 3 bulbs. It's going to split up between 4 loads. And if this one has much higher resistance, this is going to consume the majority of the voltage. So if this thing is, let's say, 1,000 ohms, this is going to take $11.75. You're going to get $11.25. You get a quarter, you get a quarter, you get a quarter. These aren't even going to light up at all. So if this resistance is not that high, they'll be dim. But if this resistance is really high, they'll be out. They won't even be on. Make sense? So this resistor is unseen. You know, it's apparent when you have a bulb in there, the bulb is on, it's glowing. But when it's corrosion in the circuit, when it's these types of things, it's like this, but you can't see it. And in the car, it's buried behind some panel, in some connector, right? So really when the car comes in, they're mostly going to say like, oh, these lights don't work. And then you could say like, well, let me do some troubleshooting. Cool. So if we were to do troubleshooting and you were to show 12, 12, 12, 1175, 1150, 1125, you'd be like, these aren't dropping all the voltage. That means something else is consuming the majority of that voltage. That's unwanted circuit resistance. Make sense? And then we would track it down. So you'd say like 1175, and then if here you go to 0 volts, you know that it's this. But if you're blind to that, if you can't see that, and you think it's just this wire going to this point, and you measure 1175 going into the wire and 0 volts coming out of the wire itself appears to be consuming 11, whatever the number was, 1125. A wire should never be dropping that much voltage. Make sense? Then you'd say, well, we got an issue on this wire. You dig a little bit further in, and you'd find someone soldered a resistor in there just to mess with you. Maybe. Probably not. You probably find some wire damage, some corrosion in the connector, a wire that, like I told you that story of the razor blade that cut the insulation and then the oxidation set in on the copper, right? If you understand this concept right here, you can fix cars. You don't get to look for this though. It's not presented to you on a beautiful board. It's like, it's the car, the harness is behind here, it's over here, it's up there, it's down there. But if you can predict your circuit voltage drops, and you can be like, I'm not getting the right voltage where I'm supposed to be getting it, you can interpret that there's unwanted resistance. You can determine where the unwanted resistance is. If those bulbs are dim, you can be like, oh, it's got resistance. Where? At the battery, at the fuse, at this wire, at this bulb, at this wire, at this bulb, at this wire, at this bulb, at this wire, or at this wire, or at this switch, or at this ground. Remember the first question earlier when the bulb was dim and I asked where the resistance was and I got a couple answers? They were good potential answers, but to really diagnose it, to sell a repair, you have to pinpoint it. And so that's what you guys were doing out there. So if you got all the way to the resistor, great. If you didn't, after break. Okay, that's fine. Cool. So like, again, summarizing some of the problems that we see: high resistance, we talked about that unwanted resistance. An open, what's the difference? High resistance and open.
High resistance.
The same.
So if you have high resistance, it might just be like that resistor's in there and it's 10 ohms. The mouse chewed a wire and it's 100 ohms, 1,000 ohms. An open is going to be like millions of ohms. So in a way, they're kind of the same. But the way we want to write it up, remember, to justify our time, it needs to be accurate. So an open wire is going to be a wire that's like broken. Makes sense? Sometimes they don't look broken. Sometimes the copper breaks apart inside the insulation and it looks like it's okay, but we measure that it's broken. Unfortunately, you can't, maybe you get a good enough microscope, you don't get to watch the electrons go through and be like, oh, there, the electrons are stopping right there. You know, like you have to measure. An open would be 12 volts, 12 volts, 12 volts, 0 volts. It's open. A high resistance would be 12 volts, 6 volts. See what I'm saying? See how the high resistance is not a full entire voltage drop, it's some of it. Cool? And then a short to ground, back it up. What happened here? Trace it. 12 volts comes in, 12 volts goes through the first bulb. You expect it to drop about 4. You expect this to drop 4. That means there should be about 4 volts left over. And then we run a short to ground. That's interesting. What do you think would happen? So short to ground in a series circuit can give you results you didn't expect. Now, if I were to redraw this and I were to take this and short it to ground, what would that do?
No resistance. No voltage for anything else.
True, but you were right about something. No real resistance. Look at the circuit. The fuse has very little to no resistance. The wire has little to no resistance. And this wire has little to no resistance. So overall, if we were to do that Ohm's law, do you remember that? Remember, our source is 12. This is V. This is A. This is R. What's our overall resistance just right here? Nothing. It's like basically nothing. Remember that 0.1? And then you do, cover this, 12 divided by 0.1 was, do you remember how much? 120 amps. Yeah, that fuse is nuked. You put that fuse in the microwave and left it there for the whole week. Like, so a short to ground before the load where the 12 volt goes to ground, that blows the fuse. But this one's different, right? This one's way different.
Broke every bulb in its body.
So this one, we shorted to ground. This bulb was supposed to drop 4 volts, but how much does it, this bulb, yeah, was supposed to drop 4, right? 4, 4, and 4 is 12. How much is it actually going to drop with the shorted wire in there? Because now there's only 2.
About 8.
6.
6 and 6, and then it goes to ground. What does this one do? Nothing. All the path of least resistance can be like, no, we're not going to go through an added resistor. We're going to go straight to ground right there. What happens when you turn the switch off? You open the switch, right? What happens on this short to ground when you open the switch?
Nothing.
It doesn't change. These 2 lights are on. You turn the switch off. These 2 lights are on. You turn the switch on. These 2 lights are on. See what I'm saying? So we've lost control of the circuit because we have a short to ground right here that's bypassing a switch. So you guys did some of these circuits several weeks ago. You notice the difference? The switch isn't up here. You have the switch on the ground. This is ground controlled. So when you have a short to ground and a ground controlled, it basically just bypasses the switch and or maybe a load or something, and you lose control of the circuit. You can't turn it off. You guys ever seen a car, the tail lights or the brake lights are stuck on? I saw one just last week. Brake lights were on, brake lights were on, brake lights were on. It was in the parking lot with the key off and the car was locked and the people weren't even there and the brake lights were on, right? That's like short to ground. Now in that car, actually, probably what was wrong was the switch was stuck closed. That can happen too. The switch is stuck closed on the brake lights is usually because of an adjustment that was messed up. So that's a good example of a short to ground. Then, you know, when we talk about the troubleshooting, you've got several different tools that you have available to you. So voltage drop would be one. If you guys will recall the voltage drop, here's my orange one. Voltage drop is the T-Rex arms. You know a fuse should drop no volts, so just check component. Fuse no volts, switch no volts, dimmer no volts. You're like, wait a minute, the dimmer's a load. The dimmer shouldn't be dropping 0 volts. You already know there's something wrong in the circuit. And then you measure the wire, and the wire drops the full 12 volts. That's how you could test for an open using the voltage drop tool available to you. What about the available voltage tool? You know, we talked about that. The available voltage tool is another good tool. We hang the ground in the ground, and then we see what's available. 12 from the source, going to the fuse. 12 after the fuse. Side question, how much did it drop? From 12 to 12, it dropped what? Nothing. It's the same as this, right? It's just 2 different ways. Which tool do you want to use? You want to do T-Rex arms voltage drop? Cool. Put them like this, and it drops 0. Or you want to do available voltage? Put it like this. It had 12. It still has 12. It dropped 0. It's 2 different ways to do it, right? So with the available voltage, we have 12, we have 12, we have 12. Whoops. What do you expect to have after the dimmer? We should probably drop something. Isn't the dimmer the load?
Yeah.
But you still have 12 after the dimmer. You're like, wait a minute. Why do I have 12 volts after the load? I should have something like 6 depending on the specific resistance, right? But I shouldn't have 12. I know there's something wrong. Then I go to available voltage after this wire, and I'm like, wait a minute. I had 12 volts going into the wire, and I have 0 volts going out of the wire. That wire is broken. The wire's open. It's, again, this is how you actually fix the customer's car. Which do you want to do? Voltage drop or available voltage? It's up to you. I want you to be able to do both. I want you to be comfortable with both. I want you to be familiar with both. There's a time and place for each. So let's say it's like a Suburban, and you want to check let's say you want to check the brake light circuit, and you want to see how much resistance the whole circuit drops. You know that Suburban is going to be 20 feet long. Your leads can't do that, right? So at that point, you can get the extensions, or you might say, like, you know what? In this case, let me do voltage drop. And you just say like, go to the switch, voltage drop the switch. Make sense? Go to the bulb, voltage drop the bulb. So you need to be essentially like bilingual in available voltage and voltage drop. They can be confusing when you're new. So this is going to be followed up with a lot more practice, okay? A lot of practice. Cool. Another method you may consider, if you have an inoperative load, let's say a bulb, where do you want to start testing? Sometimes what we want to do is just go like right to the middle of the circuit. Just be like, how much is available at the middle? Boom. How much should it be available right there? Well, you have to have printed the diagram, traced the diagram, or at a minimum interpreted the diagram and be like, oh yeah, if this is 4 ohms and this is 4 ohms, I should have 6 right there. If I go ahead and I put the meter right there and I get 12 volts, should I have 12 volts right there? But see, the fact that I have 12 volts here tells me everything I need to know. It tells me that the problem is after this. If I were to put available voltage here and I had 0, where's the problem? Up here, exactly. So the split half method is just a way so that you know, are you going towards the front of the car, or are you going towards the back of the car? Right? Start right in the middle, boom. Oh, I'm going towards the back. Because again, remember, that's why I told you the whole story, but you got to justify your time. This is not a career that's like McDonald's where it's like, you know, you mess the order up and the customer just comes back around and you're like, oh, I got to remake your order, like, and you clocked in the whole time. It doesn't work that way. If you're messing up, it's going to be hard for you to justify your time, and there's got to be some level of accountability. So you don't have any business testing all up here. If you did the split half method, you're like, no, it's down here. Don't be playing around up there. Don't be remaking the order and milking the clock and, you know, there's whole full-on memes about all that, huh? Memes about, you know, you use the bathroom at work because you get paid to use the bathroom. Like, if you're like that, this isn't going to work out very well. I'm just letting you know. Okay, and I know they're memes, right? Because spell it. How do you spell it, Mimi? No, spell it. Spell it. Spell it. Spell it.
M-E-M-E.
That's what I thought. I know they're memes, but it's spelled like Mimi. Okay, so if you did the split half method, you could also split it in half again. Right, so you could do half, half, half. You're just trying to isolate where the real issue is. Now this one's the voltage drop. Actually, sorry, this one's on resistance, because remember, you got available voltage drop, but you also have resistance that you could use, which remember, resistance can also be kind of called continuity. Continuity meaning good continuity is low resistance. No continuity would be like a lot of resistance, like an open. Cool? So we could change our meter over to ohms, and we could basically put the red lead at the end of the dimmer and put the black lead at the end of the wire. And Tim was right, it's nice when you have it on the beeping function. Because if there's good continuity here, what will the meter read and what will the meter do? It would read like how many ohms? OL is an open. Let's say this open wasn't here. What should it read? I got you now. Not voltage. Resistance. Let's say we took a meter and you measured a good wire. It shouldn't have much resistance, am I right? And it should go beep like this. But if you took your meter and you put it here and here and it didn't go beep and it said OL, what do you have? Exactly, right? So 3 different ways that we just found this open. You could use each one of the tools depending on what you're trying to do. Or the other thing is, you know, I'll be honest, sometimes, you know, when you're problem after problem after problem, your brain gets a little fried and you're sort of like, I'm pretty sure this has a bad harness. And let's just say it's a non-repairable, like an airbag harness. You know, an airbag harness, you're not supposed to repair those. You're supposed to replace the whole harness. That can be several $1,000s. If I just did some voltage drop testing on airbags and I'm like, oh, the harness is bad, it's going to be a $3,000 part. I'm fine with retesting it in another way just to boost my confidence and be like, is this airbag harness really bad? Let me change it over to ohms and be like, yeah, this airbag harness is really bad. I'll be like, available voltage, it's bad. Voltage drop, it's bad. continuity test it's bad, and they'll be like, yeah, hey, this harness is bad. And they'll be like, are you sure? Because this is going to be $3,000 in parts. And be like, man, I tested it 3 different ways. I'm sure. You know, that's a big deal. So it's nice to be able to use multiple tools to be able to confirm and kind of double confirm. Even though, to be honest with you, if it fails voltage, available voltage or voltage drop, this is redundant, but still good to know. And then here's like, for example, here would be a short. If this was the case, how does this car arrive at the shop? What would the customer come in for? I guess I got to give you a little more info. Let's say this is headlight. Let's just say it's a motorcycle. It's only got one headlight though. So if this was the condition with the circuit, what would this condition cause?
The headlight was on.
Would it though? Because,
Before the load.
oh yeah, before the load. So see, but you were right. If the switch was on the ground and the short was on the ground, then it would keep it on all the time. But see, this short is before the load. So if you trace it, you got 12 volts right here. You got it going through a fuse. You got it going through a switch. And then it's like, there is no load. I go straight to ground. That's when you're, exactly. Customer comes in with a blown fuse and you're like, oh, I know what's wrong with your headlight. It's got a blown fuse. I know because I took it out and I looked at it. And then what do you do to fix it? Put another fuse in. You know what happens immediately? Crack! You can hear them too. They make a snap sound. So you know what you do? At least a couple more. Snap, snap, snap. So if I see a tech with a big old pile of blown fuses, I know they need to bring it on. Come on back to school, okay? So there's different ways to troubleshoot this, but, and we'll talk about it actually a little bit right now, but the main thing is, if that fuse is blowing, there's too many amps. One of the real possibilities is it's shorted to ground. You have several ways you could test this. You know, to really test it, you could do available voltage. You can be like, what's the available voltage here? It's going to be 12, but after the fuse, it's going to be 0. So you're going to be like, oh, it's a blown fuse, and you get stuck in the loop like, it's a blown fuse, it's a blown fuse, it's a blown fuse. So probably a good way to test it, if you were to disconnect power, couldn't you use your meter on resistance and put your black lead on ground and put your red lead on the fuse? And if there's good continuity, what's that tell you? It's got a connection to the ground. Should it be 0 ohms to ground? If it's 0 ohms to ground, that's your short, right? So from the textbook, we open up the page and it'll be like, oh, measure the continuity between ground and the fuse, you know, measure the resistance, put it on ohms, and it should have at least, they'll give you some number, you know, at least 10 million ohms or something, 10 mega ohms or 10,000 ohms. They'll give you some number. Cool. And if you have 0.0, you're like, oh, wow, it's a short. And so if you have it on ohms, or let's say even better, you put it on the continuity test, and that's ohms where it beeps at you. So if it's going beep, then the next thing you could do, you ready for this? You can disconnect stuff. Cool. So if you were to have it go beep and you disconnect the headlight and it doesn't change, that means it's before the headlight. Then you disconnect the dimmer and it doesn't change, that means it's before the dimmer. And you disconnect the switch and it stops beeping, and all of a sudden there's a lot of open, you know, there's a lot of ohms, there's no longer continuity. You're like, oh, okay. Here it was no beep and here it was beep. It's between the beep and the no beep. It's between the dimmer and the switch. That's a way to isolate where the short is. Make sense? Kind of, or no? A little bit. It's a lot of information right now. So I'll run through it one more time. Cool? Your meter is on ohms. Right now I have 0.0 ohms. Is it safe to say that that's shorted to ground? It's got no resistance between the power source and the ground. I disconnect the headlight. I still have 0.0. It's still shorted. I disconnect the dimmer. It's still shorted. I disconnect the switch. It goes to kiloohms or mega ohms. It's no longer shorted. So it's shorted with the switch connected right here, but as soon as I disconnect the switch, the short goes away. Can you tell that it's right by that switch right there? right? If it was right here, me disconnecting this and reconnecting it would have changed the beep or the no beep, the short or the not short. So that's the by the book way. Okay, cool kind of with the by the book way, because we are going to do that test later today. Now there's another way.
I have a question.
Go ahead.
What will make it short?
Let's say anybody like aftermarket radios. Let's say you take it to my buddy Sparky's 12 volt and audio systems, Sparky. And he's like, oh yeah, we need a big amp right here. And then like, let's get the self-tapping screw. And that self-tapping screw goes through your metal right here. It's a Phillips, in case you can't tell. And it goes right there, and it touches that wire. Now that wire is connected to a metal screw, which is going through your whatever, your interior panel or something, whatever, that could happen. Let's say another way, you have a wire and it becomes chafed, right? We rub the insulation off and it's laying right on a piece of metal. That's another short. Usually when mice chew, it's opens. They don't usually make shorts, but there's probably some other instances where you could have a short. I've even seen connectors that get totally full of water and now there's a short because the water is a decent conductor, right? But that would be that would be an example of a short. That would be how you'd find it by the book. Now I'm going to tell you something that's going to trip you out. All right, the way that we find it, we don't have a big pile of fuses if you know what you're doing. Another way you could find it is you could use like a high resistance headlight. Okay, you ready? And you could take your headlight, and this is your blown fuse, right? You pull the fuse out, you probe a terminal in right here, and you run it through your headlight. You make your own janky headlight connection, like with your own wires, and you solder little things on, or you make spade terminals or whatever. Then you run it right through here. If this is 12 volts up here, and that headlight, okay, actually, let me reword it. If it's 12 volts up here and this is shorted to ground, what's the status of that light? I've got 12 volts available, and do I or do I not have a ground right here?
Yeah.
So the headlight's on, isn't it? Why isn't it not melting the circuit? Because I took the fuse out. Exactly. We added the headlight you added becomes the load of the circuit. So you preserve that circuit by adding a high resistance headlight. And you can't short it because there's a resistor that you added. Make sense? So you basically disconnect the fuse. You could also spend the money on a short finder and stuff, and the short finder kind of does the same thing, but you could rig it up with a headlight bulb, let me tell you. So if you put the bulb in place of the fuse won't blow the bulb will light because it has 12 volts here and ground here. A fuse should not be having 12 volts and ground. That fuse is going to be exploded. Cool? So then from there, you disconnect here, the light's still on. You disconnect here, the light's still on. You disconnect here, the light's still on. You disconnect this, the light goes off. You know if you disconnected this, it's after this, but if you disconnected this and it didn't change, it's before it. So you know it's between these two. No change, it's between the two. Cool, and then you're like, oh, let me find that. And then you start wiggling the wire around, and then you're like, hey, the bulb flickers when I wiggle the wire right here. And then you're like, oh, it's chafed, and there's the ground. Every time it touches the metal, it lights, and every time it pulls away from the metal, it doesn't. Cool? So shorts aren't, nothing real crazy. Depends on where they're at. It could cause something to stay on. It could cause a fuse to blow. Depends on where the short is. So we talked a little about isolating, but if we had the blown fuse, stop stabbing new fuses in there, even if they're cheap. The headlight, that's a good way. And then just showing you disconnect. If you disconnect here and it's off, and you disconnect here and it's on, it tells you that it's between those 2 points. Just kind of what I was saying. So now you can see it's not just, this is not from the textbook. Let's just put it that way. But this is from a reputable source. More reputable than me, you know, like I have to be held to accreditation standards, so it's helpful when I can cite my sources. You guys remember in school, you gotta cite your sources. You're kind of not really allowed to like just say what you think. So this isn't, what I just said is not my opinion. This is from a particular manufacturer saying that that's a good way to troubleshoot it. Cool. And so let me do a quick check. Yeah, we're still okay. This one, if we're measuring series stuff, one of the things I want you guys to get in the habit of doing when we're doing these predictions, go to the source and trace it, right? You guys see the positive right there? We should have 12 volts. What should we have going into the fuse? 12 out of the fuse, 12. Going into the switch, 12. What about after a switch in this condition? 0, exactly. Now, we don't normally test the system with the switch closed though. I mean open. Like if the headlights don't work and you want to test them, you know you got to turn the headlights on. That means you got to connect the switch. So if the switch was open, I'll just do a sub lesson. What should we have right here if the switch is open? 0, and that's why I brought black. Okay, so what I would do to trace this, if the switch is open, I do this, and then it's real easy for me to do quick measurements and be like 12, 12, 12. Well, if I had 0 right here, I'd be like, wait a minute, I shouldn't have 0 volts on an orange highlighted wire. Makes sense? So I'm selling you on why we do the tracing. Now, more realistically though, I gotta tell you, the switch is gonna be closed. Okay, so if the switch is closed, what should I have coming out of the switch? And it's okay, we know it might drop 0.1 volts or something, but we don't really care that much about 0.1. Like if it's dropping pennies, I'm moving on. I'm moving quickly. Yes, you might have 12.6, 12.6, 12.5, 12.5, 12.3, like whatever. I'm gonna call it 12 because I'm rolling. You know what I'm really looking for? If we have right here 12.5, what am I looking for after the load right here? Yeah, I see some hands. Don't be shy to speak up. After the load, what should I have? Well, there's only one load. So it should drop. It should go, remember in a series circuit, the total of the voltage drop should always equal the source. So if I started with 12.6, by the time I get to the load, I should really drop just about all of it here, except for a couple pennies along the way. Okay, I'm okay with losing a couple pennies along the way, but I should drop about 12.6 here, which would leave me with about 0. Cool? That I care about, which is why when I highlight this, I'll use green, so I'm good. This is green, ground. This is 12. And that's really what I want, and that's it. Okay? If I were to measure 0 right here, is that a good measurement? 0 right here?
No.
No. So I'd be like, wait a minute, something's wrong. What if I were to measure 12 here, and 0 here, and 12 here, and 0? If it's closed, yeah, see I drew it closed. 12 here and 0 here. Switch is no good. Bingo. That'd be test and available. If I wanted to test it with a voltage drop, that's what V3 is doing. Would you agree? So now we're saying V1, what is V1 as a voltage drop really checking? Can you tell that's a positive to negative terminal of the battery? That's considered checking the source. Then what are we testing with V2 right here? The fuse. And what should we drop on a fuse? About nothing. And what are we testing with V3? The switch. And what should we drop? Very little. And then V4, what's V4 testing? And how much should we drop? Bingo. Done. Over, and it's so repetitive. Like when you get to that point and I see your little light bulb go off, you'd be like, oh, then I know you got it. Then I know you're there. Okay, so now if you were to get some random, number, like let's just say you got, rather than a 12.5, let's say you got like a 7.2 or something. What do you think would cause a 7.2 to be available at this point?
The switch is wasting the.
It could be, but do you know that? It could be the wire, it could be the switch, it could be the wire, it could be the fuse. See, so that's where we need to do our tests. Now, if I got 7.2 there and I come back here and I'm like 12, 12.0, 12.0, 7.2, 7.2, 7.2, 7.2, 12.0, 7.2, 7.2. What was the problem? Something's weird with that fuse. Like fuses typically don't drop, 5 volts, but it doesn't matter. Like that's the test. The test is the test. Makes sense? You'd hunt it down and be like, why am I dropping voltage on a fuse right there? I shouldn't be dropping voltage on a fuse. Cool. Then you'll get to the point where you always know where the voltage is being lost, and you always know that's your problem. You know what to sell. You know, if it's a wire, you may be like, hey, you're dropping voltage on a wire, but I really need to open your harness up and spend all this time tearing it down to tell you exactly what's wrong. But some people will just say, you're dropping the voltage on the wire. I'm selling you a harness for $3,000. Have a nice day. Depends on who you work for. That's not exactly your call, by the way. Okay, and so this is kind of more of the same, but there's just a slight change. Now you have 2 loads. So if we were to trace this out, let's do it together. 12 volts at the battery. What do I expect going into the fuse? So I can do that. What do I expect coming out of the fuse? 12. What do I expect going into the switch? I'm going to close this switch. Right, they always have to show you the switch so it starts open, but we're testing it with it closed. Going into the switch, 12. Coming out of the switch, 12-ish. Going into the first load, 12. Coming out of the first load. Tricky, huh? I'll give you a clue. It's 3 ohms and 3 ohms. So, twins. What's this one what are we gonna have coming out? 6. 6. How about this one? 0. Exact. That would be correct. So how we would end up doing our predictions would be like, well, you got to know how many, loads are in the series circuit. Okay, just drive in series. Series, they share. Series, they share. Okay, kind of get it, hopefully, because we're about to switch it up on you. Okay, I think we're really solid on those. We can always come back and do a little bit more practice, but before I do, I want you to recall in a parallel, they're commonly used, in different things. So like, let's say you had 4 tail lights or maybe 4 parking lights or something. This would be normal. It's a couple things. The resistance decreases when more parallel paths are added. Current flow from individual legs always add up. The voltage stays the same. Let me break that down for you. If we have 12 and we have 12, how much does A1 have available to it? Now we have 4, so do we need to do complicated math right here? No, it gets 12. Guess what this one gets?
12.
They all get access to the full available voltage. See how that's so different? When it's in parallel, they're not sharing. Make sense? However, if they're all getting access to the 12, what is different is the amps. Make sense? So now, if you were to do the actual measurement for every one that you add, overall you're adding a lane, it lowers the overall resistance. Then if you were to do, more detailed Ohm's law, you'd find like, let's say, we won't even use these. Let's just make it super simple. Like we were saying before, if this one had 12 ohms, we'd have a source voltage of 12. You have a resistance of 12. To find the amps, what's 12 divided by 12? So if we have 1 amp, 1 amp, 1 amp, 1 amp, how much is coming through at 5? 4 amps, exactly. That's how, it's really not complicated, but you just have to understand, like, for every one you add, all the cars going through here, we're all going on the same road back here. Make sense? Kind of, sort of, ish?
Or those have to be equal to the amount of amps that it's pushing.
They determine it. So let's just say I did, let's just say I changed it and I made the resistance 6. If I made the resistance 6, how many amps would that be? What's 12 divided by 6? 2. So now we wouldn't have 1, we'd have 2 and 2 and 2 and 2. So what would be flowing back here?
8.
8 amps. 8 amps, yes, 12 volts, but 8 amps, right? So it depends on what you're kind of looking at. Make sense? So again, it's just looking at it like how we're looking at it. It's not really that complicated. Now, if you had to engineer it and calculate it and all that type of stuff, that's when you do the Ohm's law. And I'm even going to just avoid that math. I'm not even going to go there because this is the more practical. Car comes in, this bulb doesn't work. Now, this is way different than series. Right? If that bulb doesn't work, let's think about what measurements we absolutely need to do if these 3 are bright. Where should I start measuring 12 volts here? You can. 12 volts here. What should I have through the switch? 12, 12. What should I have going into this? Sometimes we'll call this a splice. 12. What should I have here? 12. I should have 12 here, right? But we kind of already know that if this one's not working, but these 3 are bright, we pretty much know we have 12 here. I'm going to start my diagnosis somewhere between here and here. I know my problem is between these 2 points. Do you understand why? This is the only one that doesn't work, and all these are bright. So now, let me take this. This seems more complicated, but let me make it more simple. I would ignore all this other stuff, and I would literally just look at this circuit. We have this. We have a wire going down. There's an A2 right here. That's an ammeter. It leaves that. It goes through and then it goes to ground. That's your whole circuit. Guess what? What type of circuit's that? That's a series circuit. We know how to do those. See, so like when we want to troubleshoot a parallel, mainly what we're dealing with is opens, shorts, high resistance. You're pretty much just going to take the section that is relevant and diagnose that one. Kind of make sense? Really not that complicated. I believe that you could do it. And so we will get into parallel stuff a little bit more. Cool. Let's say, somebody time check me. What we got?
12:30.
Okay, so we got a little bit of time. Yeah, I heard that. Wrong time zone. All right, so check this out. Man, that heat came on warm, huh? Okay, so let's just say here we are back at this customer's problem. This light glows. Guess probably orange would have looked better. This light glows. This light doesn't. What can we determine? You think it's a bad fuse? Because this one glows. You think it's a bad switch?
No.
Why not? Because this one glows. If the switch was bad, it would be like this. 12, 12, 12, 0. This one wouldn't glow. Make sense? Agree with me? So if that one's glowing, we pretty much already know this one's got 12, and we pretty much know this one's got ground, which means I can say for sure this is good, this is good, this is good. I can say for sure this is good, 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 this is good. So where's my troubleshooting actually occurring? Lamp 2. Let me draw it for you. It's really complicated. There's a splice. That's where the wires join. Comes down and it goes to a bulb. Looks like this. Goes down like this and there's a splice. If you can't do that, I'm doing something wrong. Because if you're here and you can't do this, there's something wrong there. So I just be like, oh, well, let me see. I should have 12 here. I should have 0 here. What don't I have, right? And boom, like such an easy diagnosis. If I don't have 12 here, where's the problem? It's right here. If I don't have 12, let's say I have 0. Couldn't be the switch though, because that one works. I'm only looking at this circuit. It's got to be, if it doesn't have 12, let's say I do my measurement and it has 0, my issue's between here and here, and that's it. Or if I do have 12, and right here I don't have ground, where's my issue? Then my issue is just between here and here. That's it. I'm not worried about here because this one works. I'm not worried about here because this one works. Make sense? That's how we really are going to troubleshoot that. It's pretty simple. If it's a car with taillights and one taillight's out, it's going to either be the bulb, the connection on the positive, the connection on the negative, the wire on the positive, the wire on the negative. That's it. That's all you got. That's it. It's just one of those. So we could voltage drop it, couldn't we? How do you voltage drop the wire? Like this. What should I voltage drop on the wire? How much should I drop? Nothing. How much should I drop on the bulb? 12. How much should I drop on the other wire? You could do 3 tests and diagnose what's wrong with that. So simple. Yes? No? Yeah. Absolutely. Okay? And that's kind of what this is showing, just summarizing our tests right there. Voltage dropping. Cool. You could also do it in ohms. So if you wanted to diagnose that circuit, you could literally put the meter on ohms. About how many ohms would you expect between here and here? It's okay if you don't totally know, but a bulb. Bulbs might have 4 ohms or 24 ohms, but it shouldn't be OL, should it? If it's OL, you know that there's some open. What if I were to do the resistance right here and this were to be OL? What's wrong? Open where? In the wire, exactly. What if I were to do this resistance reading and it was OL? Open in the bulb. What if I were to do this wire and it would say OL? Open in the wire, right? So you should be able to really determine pretty quickly what are we selling this customer with just a few basic measurements. Cool. Now, the current measurements, and this is where it is different. So if we were to go, it depends on what you want to measure. If you want to measure the total circuit the total circuit amperage, that's talking about more like up here, right? If you're worried about your fuse, you need to measure here. If your fuse is blowing, it's not helpful to measure down here, right? This is the total circuit resistance, and then down here is like the branch, right? So this would be branch 1, this would be branch 2. You may have 4 branches. But then up here, you could break this open and measure the total amperage. And let's just say we had 4 amps. What do you kind of expect to be flowing on branch 1? If we have 8 amps of cars going through here, how's there only 2 way up here? So now probably more like, well, it depends. There's only 2. So if these are equal and there's 4 total coming through here, you probably have about 2 going here and 2 going here. That makes sense? So you guys know when you're you ever been in like a 1-lane road and then all of a sudden it splits into a 2? So if you were to go forward to the 2-lane and be like, oh, there's 4 cars that have gone by, but if there was 2 cars in this lane and 2 cars in this lane, if you were to back up to where it was 1 lane, how many would there have been? There was 4 in 1 lane and then they split to 2 and 2. That equals 4, right? Exact. So here you'd have 4 amps and down here you'd have 2 amps and 2 amps. They always have to be, the branch circuits always total to the total. Make sense? So if we had, how many do you want? I don't know. Let's do more. If I had 4 amps and these are all the same resistances, how much do you expect in each one of these lanes? 1, 1, 1, 1. Exactly. There you go. Yeah? Okay. Not so horrible, but you see how that's so different than series? On series, every bulb that you add, it just slows it down more and more and more. And your total resistance, or your amperage is the same through the circuit on a series. On a parallel, it's not. On a parallel circuit, your total circuit amperage is the sum of all your branches. Yes? You love it. Okay. So right here, when you guys get back, we will be building these. So this is pretty pretty good point actually to break it off. So when if you guys want, you should get a picture of this, because this will be the next thing you build, and I'll get you that packet. And then we're gonna call it good.